Hi, welcome back to the problem solving section for Calculus 3. We are continuing work on the Stokes theory. And our part 1 video, we talk about how about, when you try to, so this become a very complicated. If you want to use a surface integration, and it will become very complicated. And so then maybe you can get a rescue by using the line integral. So today we are going to do these directions here. So, the problem asks us to find the line integrals, but it turns out the line integral is very tedious or difficult to find. So maybe then we can use the curl idea to do a surface integrations here. All right. So now let's take a look. So what type of the problem we'll look at by using the surface integration to try to find the line integral issue? All right, let's take a look at this problem here. All right. So I want to find the line integrals here, right? So this C is the, counterclockwise or the orientations here, right? So let's take a look. You give me a vector fields here. And the C is the boundary of a part of the plane 3x plus 2y plus z equal to 1 in the first octane. All right. So how do I find the line integral? So let's take a look at what is this one telling us. All right. So this one's here. If this is my, okay. So this is x, y, z here. All right. So this is x, y, z. So 3x plus 2y plus 1 equal to 1. So when x, y equal to 1, z equal to 1. So this is 1, this is 1. So this is 1/3. So when the y and the z equal to 0, x equal to 1/3 here. All right, so 1/3 here, here. When the x and z equal to 0, y equal to 1/2 here. All right, so here, let me put a different color. So this is here, here 1/3. This is 1/2. All right, so this is 1/3. This is 1/2. This is 1. So my, so here, okay, so this will be the, okay, so this will be the surface. So they said is the boundary part of the plane, the first octane. So this is my surface S here, right? So the boundary, okay, so let's try to write down the boundaries here. So the boundary is here, right? So it will be counterclockwise. So this is the boundary and this is the boundaries here. This is the boundaries here, right? So if I want to find, okay, so remember, right? So if I want to find, integrate FDR, all right. So in fact, in here, because I have 3, so I have a C1, C2, C3. So I need to create 3 parametric equations, then substitute back to my FCFDR, and then integrate 3 times. That is why I said for this type of the problems, maybe instead of using the line integral and do the line integral 3 times, special right now we need to do what? I need to do like find the parametric equation C1, find the parametric equation C2, find the parametric equation C3. So maybe, so instead of doing that, let's take a look. How do I use the curls series to do that? All right. So, okay, so now let's do the curl. So it's one more time. We did this many times. So we should, so the curl F should be, so this is IJK, right? All right, so this is row the row X, row the row Y, row the row Z's, right? So Y here is 1, then this is X plus YZ, and this is XY minus square roots of the Z. So let's put the first 2 column out, row the row X, 1, and this is row the row Y, and the X plus YZ. Okay. And then we do ding, 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 and minus here, ding, ding, ding. Okay, so let's take a look. What is my curls here? So this is row y here. So first one's here, take the derivative of y, so you will have x, right? So this is I components, and then this is take the derivative of the z is 1, so it's 0, j, and then k is row k, no, row x, so x, so it's 1. So times k, so this is my red one, then minus my green one, so this is row x, row y, row 1, so it's 0k, and minus the row z, so row z will be y, this is I, then minus the row x here will be yj here. Okay, so now I combined, so x, okay, so x minus y, so this is my I components, right? Then my j, I only have y j components here. Then I have a k here, right? 1. 1 is my case here. All right, so this is the equal. This is the equal. I can put it into vector form. So negative y. Oh, then this is a positive. So positive. So 1, right? So this is equal to my curl, right? So this is equal to this vector field. And then I know, and this, so I can say this is my P component function. This is my Q components function. And this is my R components functions here. All right. Okay. So now in here, all right. So in here, let's take a look at how do I do the integration. All right. So to remember okay, so now in here I have x3x plus 2y. So this turns out pretty good, right? The curl looks nice, very easy. So the 3x plus 2y plus z equal to 1. So I can change z equal to 1 minus 3x minus 2y. Right, so this is equal to my g function xy. So I know that rho g rho x equal to negative 3, rho g rho y equal to negative 2. All right, now let's do it, right? So then I integrate the curl f dot ds, okay? So I can integrate this region D. So use which formula? We use rho P, negative P, rho G, rho X minus Q, rho G, rho Y plus R. So right, we use this many times for the surface integrations here. All right, let's take a look here. Rho, okay, so the rho negative, so it's negative X minus Y, rho g rho x is negative 3. Okay, plus negative q, so it's plus negative. No, so it's okay. So it's that should be negative. Okay, minus. Okay. Okay, so minus. Okay, let's say minus q minus negative y times what? Rho g rho y times negative 2. Okay, plus R. What is the R's here? R is once here, right? Then I integrate here. Okay, so before we simplify, let's see here. So this will give you the, so negative, negative, positive. So it's 3x minus 3y minus 3x plus minus 3y minus, so we will get and this is ones, right? So I'm going to get a 1 plus 3x, okay, minus 5y. Okay, so when I combine to do some algebra, all these things will give me this, right? Okay, so it's 1 plus 3x minus 5y here. Then I can do dy dx here, right? Because it's only dy dx. Now the next things here. So this integration turns out pretty easy, right? 1 plus 3x is here. Now the dy dx is here. All right. So the dy dx is this line segments here. Let me put this line segments into the xy plane. So maybe, okay, so this is x, this is y, right? X is from, so this is 1, so this is 1/3, and this is 1, this is 1/2, right? So this is my line segments here, okay? So these lines here will be, so in here, this line, if you put it into, so this line will be y, okay, so this will be y equal to 1/2 1 minus 3x here. So if you just put the 2-point, use the 2-point formula, you can get a line. Let's double check to see it's right. X equal to 0, y equal to 1/2, y equal to 0, x equal to 1/3, right? So I know I got it correct. This is my line equations, right? So now I'm integrating along the y. So that means from this distance up, up, up. So my y is from 0 to where? 0 to 1/2 and 1 minus 3x. All right. Then what is my dy? After you finish dy, what is my dx? My x is from here to here, right? So my x is from the 0 to 1/3 here. So then this turns out to be a very simple integrations here. So basically you can just do a, so this is 0, 1/3, and then you integrate dy. So this will be y plus 3xy minus 5 over 2 the y square. Then you input 1/2 1 minus 3x over 0. Whatever you got out from here, then you integrate the x again. So like in here, I'm not going to spend the video time to just go to the algebra. So everybody should know how to integrate these things here. So the answer for this one will be 1 over 24. Okay, so like in here, this is the opposite about to go to the other direction of the Stokes theories, right? So right now you want to find the line integrals for this boundary C1, C2, C3. You still can do that by using line integral, but then you need to create the parametric equations 3 times. Substitute, integrate 3 times. So now you'll be able to solve this type of the problems by going to find the curl of the field. Then you integrate the curls. All right, so let's take a look at here is the same things here, right? So for this ones here, this one is even a little bit more complicated here, right? So in here, this is the C is the boundaries in here, the pink one. You want to do that. So in order to do the line integrals, you will need to do the same thing like C1, C2, and C3. And these 3 segments is not line segments anymore. So to try to find the parametric equations will be even harder here. All right, so it will be even harder. So probably, to do the Stokes theory by using the curl. All right, so with the x, y, y, z, and the zk, and right now, I assume we know how to find the curl. I'm not going to go through the algebra part. So go through the curl, you do the same thing, do the IJK, those things, right? So this curl, I already calculate. This will be negative y I minus the z j and minus x k. So this curl is very simple. So this is negative y, negative z, negative x here. All right, then in here we have these functions, right? So I can say the z, so gxy is equal to 1 minus x squared minus y squared here, right? So then in here, I know the rho g rho x equal to the negative 2x rho g rho y equal to the negative 2y. Okay, so now let's see here the curl. All right, so the curl f is negative 1, negative z, negative x here. All right, so this one's here. So I say, hey, I'm integrating on this surface here, right? So the surface of the curl f dot ds. All right, so going to be, all right, so the curl functions here, right? So this is negative y, negative z, negative x here. Remember? All right, so remember this will be your p, q, and r. Sure, right? Okay, so remember the integration? So which formula we use? Hey, we use the same, this ones here. Negative p, rho g, rho x, rho q, rho y, right? That's a very, very handy formula. Okay, so now rho p, negative p, so it's a negative, negative y, and the rho g, rho x is negative 2x. You see here, they change everything back to the xy. Then minus rho q, minus q, q is negative z, then the rho g, rho y is negative 2y here, right? And the plus r, r is negative x. Wow, that's really look pretty good, right? So become d and what? dA here. Okay, so this will be d and dA here. So then you will see here, this is let's simplify it. So here, let's see, it's a negative, so it's negative, negative, negative. So it's negative 2xy, negative, negative, negative. So yes, what? So it's negative 2xy. So this is minus, oh, so here's z's, right? So the z, okay, so the z, okay, so I need to replace negative z. So the negative z is negative 1 minus x squared minus y squared. I need to change everything to xy. So this is negative, negative, negative. So it's negative 2y, right? So this is negative 2y times 1 minus x squared minus y squared. Okay, then minus x dA here. Okay, so this one's here because for here on the when z equal to zeros, right? So this this surface here, this one's here when z equal to 0 is x squared plus y squared equal to 1. All right, so because x squared plus y squared equal to 1, in order to integrate that, I need to change to the polar coordinates. So this one is a little complicated than the other, but still not too bad. So I will say that x equal to the, what here, x equal to the r cosine theta, and the y equal to the r sine theta. So remember, polar, my Jacobian, will be equal to r, right? Okay, so now I can rewrite these integrations here. Okay, so be careful here. Everything I replace with here, right? So this is going to be negative 2 r cosine theta times r sine theta minus 2 r sine theta 1 minus x squared, y squared is 1 minus r squared, right? Because x squared plus y squared is equal to, so from here I know x squared plus y squared equal to r squared. So 1 minus r squared. Okay, then minus r cosine theta. Okay, the whole thing times the Jacobian r. Then I have dr d theta. So r is from where to where? From 0 to 1. Then theta is from where to where? Because I'm only working for this surface here, right? So theta is only rotate a quarter of it. So it's 0 to pi over 2 here. All right, so be very careful. This is a Jacobian, right? So this is a Jacobian. And then this one's 1 minus r squared because it's in here, right? So because I know x squared minus plus y squared equal to the r squared. So now let's simplify a little bit. All right, so this one's here. So this is 0 to pi over 2. Then here, this is negative 2 r cubed cosine theta sine theta. Then this one is minus 2r squared, 1 minus r squared sine theta. That's right. Then here, I can minus the r squared cosine theta. The whole thing here is dr d theta. So after you change to the polar coordinates, then you find out that the integration is not that, okay, sorry, here r is from 0 to 1. All right. So you will find out the integration is not that complicated anymore. You can use software or physically carry out the integration. So I carry out the integration, and so the final answer here will be negative 17 over 20 here. All right, so that's the two examples here. How can you use the surface integration to help to simplify the line integrals? So the most of this situation happens if when you try to find the line integrals, you have several segments that you need to do. Then think about it. Each segment, you need to find the parametric equation. Then you need to substitute and integrate. So probably use the curl of that vector field will be an easy way to do it. All right, that's it. And I hope both the videos will help you to understand the Stokes series here, right? So the first ones here is to tell you if the curl of f is very complicated, it's not easy to do the integration, then try to use the line integral. Then the second part is kind of go to the other direction. If you want to do a line integrals, but the line integrals, the curves, have several different segments. Then instead of doing the parametric equation several times, you try to use the surface integration to do it, using the curl f to see you'll be able to simplify that or not. All right, that's it. I hope this is helpful for your finish all the other problems here. All right. Okay, so talk to you later. So our next video, we're going to talk about the divergence here. Okay.